Okay, so today we continue our discussion of dual spaces. Let's recall that if we have a normed space X, then the dual of X, X star, is defined to be the space of all bounded linear operators from X to the base field, K, where K is our base field, which is either the field of real numbers or the field of complex numbers. And the elements of this space, so X is the dual of X, and elements of the dual are called bounded linear functionals. So today we continue our discussion of concrete examples of duals. Examples of dual spaces. So we want to describe explicitly the duals of some standard normed spaces. The first example was already discussed at the previous lecture. This is the dual of a Hilbert space. The dual of Hilbert space is characterized by the so-called Riesz presentation theorem. Which was proved at the previous lecture, and which states that if H is a Hilbert space, then we can consider the following map R from H to the dual, so H star. This map is defined as follows. If Y is an element in our space, then R of Y is a linear functional on H, which takes little x, any element little x, to the inner product of x and y. And the theorem states that this map is an isometric antilinear bijection. Is an isometric antilinear bijection. So very roughly, this theorem means that we can, in a sense, identify H and H star. But it's important to remember that this identification is not an isomorphism, for the simple reason that it is not linear, it is antilinear. А в каком месте? Но я могу здесь поменять местами, и здесь поменять местами, это будет то же самое. А вы как предлагаете? Вы предлагаете в одном месте поменять местами? Смотрите, в чем дело. Если написать так, у нас же скалярное произведение линейно по первому аргументу. Мы хотим, чтобы R от Y был бы линейным функционалом. Да, вот. Если мы поменяем только в одном месте, то получится антилинейный функционал. Вот. А изометрия в обычном смысле сохраняет норму или эквивалентно сохраняет расстояние.
То есть норма ваш и норма функционала.
Да. Угу, угу. Well, the second example, and actually this is the first example for today, is the dual of the little LP space. So we have the following result, the following theorem. Suppose that P and Q are real numbers, strictly bigger than 1 and satisfying the following relation. The same relation as in Hölder's inequality. I claim that the map from, as denoted by alpha, from LQ to the dual of LP, which takes each element a little y in LQ to the functional Fy, and Fy is the following sum. So this map alpha is an isometric isomorphism. An isometric isomorphism. So if we start with a little p from 1 to infinity, then little q is uniquely determined by this relation, and the theorem states that the dual of LP is isomorphic to LQ, and the isomorphism is very explicit. First of all, so to prove this result, first of all we apply Hölder's inequality. And we conclude that, well, since y is in LQ and x is in LP, we conclude that this series converges. This series is denoted by star, converges absolutely. And the sum of the series, that is Fy of x, is less than or equal to the product of the LQ norm of y by the LP norm of x. And this implies that Fy is indeed a bounded linear functional on LP, and the norm of this functional is less than or equal to the LQ norm of y. So we have this map alpha, which is well defined. And we have a map alpha from LQ to the dual of LP. Given by this formula. And we want to show that alpha is an isometric isomorphism. To begin with, let's observe that alpha is injective. Well, indeed, let En denote the following element in LQ. So as usual, En is the sequence where 1 is the nth slot and 0 is elsewhere. In LP, or, well, better to take this element in LP. And we observe that if we apply Fy to En, what we get is just Yn for each n. And this really implies that the kernel of alpha is trivial. Because if Fy is 0, then this is also 0. So all the coordinates of y are 0. And so the kernel is trivial. So alpha is injective. And now we have to show that alpha is surjective and isometric. And we will prove these two statements simultaneously. So let's prove the surjectivity. We take an arbitrary functional f on LP. And we want to show that f comes from an element little y in LQ. So we want to show that Fy has this form. So actually, there is only a way to define little y. We look here, and we see that to define y, we just must substitute En to f. Let Yn be f of En. Of course, it's not obvious at all that this sequence yn is an element of LQ. Let's show that this is indeed the case. So we take any natural number, big N, and let's try to estimate the following sum from 1 to n, yi to the power q. Basically, we want to show that the series converges, and to show that the series converges, we have to show that all such finite sums are bounded by the same constant. Okay, so let's write this expression in the following form. This will be the sum from y to n, xy, yi, xi, yi, where yi is given by the following formula. This is yi to the power q over yi, if this is non-zero. This is xi, sorry. We already have y, and we define x. So we define xi in the following way: if yi is non-zero, and 0 otherwise. So if we define xi in this way, then clearly this formula is true. Okay, now what is this? So we continue this equality. So yi is f of ei, and by linearity, this is f applied to the following sum from y to n, xi ei. But f is bounded. F is bounded, so we can estimate this expression in the following way. Мы хотим, чтобы y лежал хотим сказать, что y в L лежит. Мы же этого не знаем пока.
То есть мы берем функционал, а потом пытаемся проверить, что y соответствующий этому функционалу в L.
Ну да, мы хотим доказать, что f пришел из L, а значит, ему должен соответствовать какой-то y. Где найти y? Только здесь, больше нигде. Вот мы его так определяем, а потом пытаемся доказать, что y из L. So the strategy is as follows. We start from a linear function, a little f. We want to show that f comes from little y, from here. And to define little y, we just use this formula. So if f equals fy, then yn is necessarily f of en. So we can always define yn in this way, but we have to show that y, the resulting sequence, is in LQ. And to show that it is in LQ, we apply. Okay, so we want to show that this expression is bounded by a constant which doesn't depend on n. And to prove this, we write this expression in this way. So clearly this is true. Now, since yi is f of ei, by linearity of f, we write this formula as follows. And now we use the assumption that f is bounded. So since f is bounded, we can estimate this as the norm of f multiplied by the norm of this vector. So this is the LP norm. But what is this? This is the following sum, xi to the power p and to the power 1 over p. This is the LP norm of this vector. Now we look here, and we conclude that xi to the power p is yi to the power q minus 1, multiplied by p. Okay, but what is q minus 1 multiplied by p? It's easy to deduce from this formula that q minus 1 multiplied by p is just q. So we come to the following expression. And finally, we compare this and this. So we see that this is a certain number, and here we have the same number to the power 1 over p. So after we cancel this expression in brackets, on the left-hand side, we have this number to the power 1 minus 1 over p. But 1 minus 1 over p is 1 over q. So we cancel this, and as a result, we see that this number to the power 1 over q is less than or equal to the norm of f. And this is true for any natural number n. Ну, смотрите, вот эта штука, здесь она в степени 1, вся эта сумма, а здесь она в степени единицы на p. Мы просто поделили вот на эту штуку. Мы ее сократили в каком-то смысле, мы на нее поделили. Нет, это не f представляется какая-то сумма. Это вот мы оценили, смотрите, вот эту штуку, это некое число. Мы показали, что это вот некое число какое-то, оно не превосходит нормы f умножить на то же самое число, но в степени 1 Вот. А потом мы просто сократили эту степень 1 и что получилось? Получилось, что это число, оно в какой степени оно слева останется? Оно останется в степени 1 минус 1 пятая. 1 минус 1 пятая это 1 кутая. Вот оно у нас и вышло. So this estimate holds for each n, for each natural number n. And this implies that the respective series converges. So this implies that y belongs to LQ. And moreover, this implies that the LQ norm of y is less than or equal to the norm of f. Okay, so now it's now very easy to show that f equals fy. Well, indeed, we obviously have the following equality. So f of en. So what is this? This is yn, but fy of en is also yn. So they are the same. These two functionals are the same on each element en. But now we observe that the linear span of all these elements en is dense in LP. If you have an arbitrary sequence in LP, we can just consider some truncation. So we just keep the same elements from 0 to some element n, and then put zeros elsewhere. And we get an approximation of an arbitrary element in LP by a finite linear combination of ENs. So this linear span is dense in LP. So by linearity, f and fy are the same on this linear span, and by continuity, they are equal everywhere. So this implies that f equals fy. F от n это число, f это функционал. En это значение этого функционала на векторе en. Fy это другой функционал. Мы хотим доказать, что fy на самом деле равно f. И мы делаем это так. Они одинаковы на каждом en.
То есть f это тот функционал, который мы брали, а f это тот, который мы сконструировали одинакового значения на каждом.
Да, f(y) это тот, который мы сконструировали из y. То есть мы сперва сконструировали y вот таким способом, но мы сразу вот отсюда не можем построить f(y), потому что мы пока не знаем, что y лежит в L-ку. Вот мы y построили по f таким образом, потом показали, что этот y лежит в L-ку, а теперь показываем, что f и f(y) одинаковые, что они равны. Вот, они равны на каждом n, а n порождают плотное подпространство. Значит, они просто равны, как линейные функционалы. So eventually we see that alpha is a bijection. Alpha is a bijection. And to complete the proof, we have to show that it is isometric. But this is very easy, because we already know that the norm of y is less than or equal to the norm of f. But f equals fy. And at the very beginning of our proof, we observed that the norm of fy is less than or equal to the norm of y. So this is less than or equal to the norm of y. And this chain obviously implies that all these numbers are equal to each other. That is, alpha is isometric. And this completes the proof. So briefly, once again, the idea is as follows. First of all, we use Hölderlin inequality to show that alpha is well defined. Then by using these eons, we easily show that alpha is injective, the kernel is trivial. And to show that alpha is surjective, we do the following. We start with a linear functional f on LP. Then we construct a sequence y in the following way. Then we prove by using this trick that y is actually an element of LP, or of an element of LQ. Y is an element of LQ. And eventually we use this argument to show that f equals fy. So alpha is bijective. Okay. By the way, a simple corollary is as follows. If H is a separable Hilbert space, then H is isometrically isomorphic to H star. Well, indeed, if H is infinite dimensional and separable, we already know that it is isometrically isomorphic to the little L2 space. And if P equals 2 here, then Q also equals 2. And in particular, we see that L2 and L2 star are isometrically isomorphic. But once again, I'd like to stress this, that they are isometrically isomorphic, but this isomorphism is not canonical. In the sense that it depends on the choice of an orthonormal basis. The orthonormal basis in H gives us an isomorphism between H and L2. So as a result, this isomorphism depends on the choice of a basis. And in fact, this result is true for all Hilbert spaces, not necessarily separable. But so far, we discussed only separable Hilbert spaces. So formally, the corollary holds for separable spaces only. In fact, we have a more general result, which I state without proof. I have the following theorem. Suppose that we have a measure space, X mu is a measure space, and P and Q are, as in the previous proposition, so they are real numbers, related by the following inequality. We can consider the following map: alpha from LQ of x to the dual of LP of x. Given by the following formula, it takes each function f in LQ to the linear function of phi f, where phi f takes little g, a function little g from LP, to the integral of their product. And I claim that this map alpha is an isometric isomorphism. Чего? А зачем нам сопряженное? Нам не нужно сопряженное. Мы хотим, чтобы это был изометрический изоморфизм, чтобы он линейный был. Поэтому не сопряженное. Так же, как в предыдущем предложении. Там никакого комплексного сопряжения нигде нету. Мы хотим, чтобы был настоящий изометрический изоморфизм, линейный. Вот. Вопрос может возникнуть в связи с теоремой Риса. Значит, если мы вообразим здесь, что p равно двойке, so if we suppose that p is 2 and q is 2, and we put the complex conjugation here, then what we get is exactly the Ries bijection between L2 and L2 star. But if we remove the complex conjugation from here, then we get another bijection, which is not the same as the bijection from a Ries representation theorem. It's different, but it has the advantage of being linear. Если сопрягать, то формулу для этого хозяйства можно написать, опять-таки, для случая, когда p равно двойке и q равно двойке. Если сопрягать здесь, то получится формула, которую на самом деле можно написать без координат. А именно вот, где она там? Вон она. Ну, можно и так сказать, конечно, хотя я не стал бы вообще об этом думать в терминах скалярных произведений. ЛП, оно вообще не Гильбертово, там вообще нет скалярного произведения никакого приличного. Вот. Скорее фокус в другом, что вот эта штука, ее не следует путать с вот этой, хотя они и похожи, потому что это ни от какого базиса не зависит, но она антилинейна. А это, она в каком смысле координатная. То есть если мы возьмем абстрактное Гильбертово пространство, отождествим его с L2, уже это отождествление, оно строится исходя из некоторого базиса. Вот. Но тем не менее, если это мы сделаем, то мы получим вот такой вот изоморфизм между L2 и L2 со звездочкой, который даст нам, в свою очередь, изоморфизм между H и H со звездочкой. Настоящий линейный изометрический изоморфизм. Но он зависит от выбора базиса. В чем фокус? Okay, so we have this result. In fact, it generalizes our previous theorem. Indeed, if x is the set of natural numbers and mu is the counting measure, then well, the big LP space becomes the little LP space. The integral becomes just the sum over the natural numbers, and we get our previous result. So this result is more general, but the proof is not very easy. I can leave it as an exercise for you, but the exercise is not very easy. The hard part is to prove that alpha is surjective. So a hint is to use the Radon-Nikodym theorem. Okay, and by the way, another exercise, which is closely related to this theorem. So this theorem describes the dual of LP in the case where P is bigger than 1, strictly bigger than 1 and finite. So what happens if P equals 1? If P equals 1, I recommend you to construct isometric isomorphisms between between L infinity and the dual of L1. So the dual of L1 is isomorphic to L infinity. And between L1 and the dual of C0. C0 is a space of sequences which vanish at infinity. And one more natural question is, how about the dual of L infinity? Well, if we look here, and if we look at the theorem, it's natural to conjecture that the dual of L infinity is isomorphic to L1. That would be quite natural. But this is a question to you. Is the dual of L1, is the dual of infinity, is it isometrically isomorphic to L1 or not? The answer will be given in the next exercise sheet. Okay, now our next concrete example of a dual space is the dual of the space of continuous functions of a compact Hausdorff topological space. So we want to describe the dual of C of x, where x is a compact Hausdorff topological space. This will be mostly a survey. So the point is that the main result, we described the dual of C of x, is quite non-trivial. This is the so-called Riesz-Markov-Kakutani theorem. So I'll not prove this result, but nevertheless, I'd like to at least to give you an exact statement and to explain where the statement comes from. To begin with, let's give some general measure theoretic definitions. Suppose that X is just a set, and A is a sigma algebra of subsets of X. First of all, we want to define complex valued measures on A. By definition, a measure or maybe let's state from the very beginning that we want to define a complex measure. A complex measure on A is a function mu from A to the complex numbers, which is additive in the following sense. So for each finite family of disjoint sets in our sigma algebra, the sets are disjoint, the measure of their union is the sum of their measures. So we see that the definition is exactly the same as in the case of positive measures. The only difference is that mu is complex valued. And we say that mu is sigma additive. If the same property holds for countably many disjoint sets. For each countable family of disjoint sets in our sigma algebra, we have the following equality. Measure of their union is the sum of their measures. By the way, a little remark, let's observe that this equality automatically implies that the series converges absolutely. The series converges absolutely. Actually, this is automatic from our definition because the left-hand side of this equality doesn't depend on the order of the sets AI. So this series converges independently on the order of its members, and this is equivalent to say that it converges absolutely. To work with complex measures, it is convenient to associate with each complex measure a positive measure, which is called the variation of mu. So if mu is a complex measure, then we define the variation of mu to be the function defined, denoted like this. So it is also a function on the same sigma algebra. It is non-negative, but in general is not necessarily finite. And it is given by the following formula. If A is a set in our sigma algebra, then we do the following. We consider all finite partitions of A into finitely many disjoint sets. For each such partition, we consider the following sum. So here AI is a finite partition of A. And finally, we take the supremum over all such partitions. So this is a non-negative function, but in general, it can happen that this number is equal to infinity. It's a simple exercise to show that the variation is indeed a measure. And moreover, if mu is sigma additive, then so is the variation of mu. Now we say that mu is a measure of bounded variation. Mu is of bounded variation. If its variation is a finite measure. If the variation is finite. And we have the following result, which is not entirely obvious, but I hope it is true, that if mu is sigma additive, then mu is of bounded variation. The proof is a nice exercise in measure theory. Let's now introduce some notation. We denote by M of A the set of all complex measure, or well, not necessarily complex, all k-valued measures, where k is our base field, of bounded variations, of bounded variation. And as usual, K is either the field of real numbers or the field of complex numbers. In fact, it's easy to observe that this is not just a set, but this is a vector space. This is a simple exercise. M of A is a vector space. The operations are pointwise. You have two measures of bounded variation, and their sum is just M1 of A plus mu1 of A plus mu2 of A. And similarly, the product of mu by a number C is just C mu of A. So this is a vector space. And moreover, this is actually a normed space. The space has a canonical norm defined by the following formula. So we take the variation of mu and we calculate the variation of x with respect to mu. And this is a norm on M of A. So M of A becomes a normed space. Okay, let's now discuss how to integrate functions with respect to a complex measure. In fact, we don't need this notion in full generality. For our purposes, it's enough to integrate only bounded measurable functions. The space of all bounded measurable functions will be denoted by BA of x. This is the space of all bounded measurable, I mean A measurable with respect to the sigma algebra A. So B of x is well known to be a closed subspace of L infinity of x, or the space of all bounded functions. Is a closed vector subspace. Well, it's a standard fact from measure theory that actually even the pointwise limit of measurable functions is measurable. And moreover, the uniform limit is also measurable. So it is a closed vector subspace of L infinity, and so it is a Banach space. B of x is a Banach space. We now have the following simple result, a proposition. For each measure mu of bounded variation, there exists a unique bounded linear functional, I mu, on B of x. Such that I mu takes the characteristic function of any set A to mu of A. Here chi A is the characteristic function, or the indicator of A, which is 1 on A and 0 on the complement of A. And this functional I mu is called the integral. I mu of f is denoted by the following symbol, and is called the integral. Integral of f with respect to mu. Let me write this explicitly. This is 1 if x is in A, and 0 if x is not in A. Just the indicator of A. Well, the proof of this result is absolutely straightforward. The construction of this functional is more or less the same as in the case of positive measures, as in the case of the usual Lebesgue integral. So first of all, we define this functional on the subspace of asimple functions, which consists of all finite linear combinations of characteristic functions, just by linearity. And then, by using the assumption that mu is a measure of bounded variation, we can easily show that this functional defined on simple function is bounded. So we, since the space of simple functions is uniformly dense in BA of x, we just extend this functional by continuity to BA of x, and we get what we need. And in fact, it's easy to show that this construction describes all bounded linear functionals on B of x. We have the following theorem, which is sometimes attributed to Hildebrand and Kantarovich. This theorem states that the map from MOA, from the space of complex measures of bounded variation, to the dual of B of x, which takes each measure mu to the irrespective integral, is an isometric isomorphism. The theorem is important, but it's rather easy. The proof is an exercise for you. Actually, the hint is just to use this formula. If we want to show that this map is surjective, we take a bounded linear functional on B of x, and to construct a measure, we simply evaluate this functional on the characteristic function. And as a result, we get a measure. And by using the assumption that the functional is bounded, it's easy to show that the measure is of bounded variation. And more or less, this is the end of the proof. We still have to prove that it is isometric, but it's a simple calculation to show that it is indeed isometric. And by the way, as a nice corollary, we can now explicitly describe the dual of the little L infinity space. Namely, let's consider the space of all complex measures on the sigma algebra of all subsets of the natural numbers. And we have the map from this space to the dual of L infinity, given by the same formula. And this is an isometric isomorphism. So the dual of L infinity, of the little L infinity space, is the space of all complex measures, but I'd like to stress that we consider finitely additive measures, not necessarily sigma additive, the space of all finitely additive measures on all subsets of the natural numbers. And by the way, if we ask how about sigma additive measures, the space of sigma additive measures on the sigma algebra is identified with little L1. L1 becomes a proper subspace of this space, and it is identified with a subspace of sigma additive measures. This is an exercise which is actually almost trivial, because to define a sigma additive measure, you just have to assign a measure to each point, to each natural number. So everything each such measure uniquely corresponds to an element of the little L1 space. Okay, this is very nice, but this is not exactly what we wanted to discuss, because our main goal now is to discuss the dual of the space C of X of continuous functions on the compact Hausdorff topological space. Okay, so from now on we assume that X is not just a set, but is a compact Hausdorff topological space. Да, да, ограниченные последовательности, конечно, полные. Тоже полные, все они полные. Конечно, аддитивные. То есть они не предполагают сигма-аддитивные. Вот это вот m, вот здесь, вот, когда мы определяем m, мы рассматриваем все меры, не только сигма-аддитивные, но вообще все. То есть сигма-аддитивность здесь нигде не используется и не нужна. А сигма-аддитивные, они как раз это те, которые из L1 пришли. То есть если мы возьмем последовательность из L1, суммируемую по модулю, да, там, скажем, x1, x2, x3, x4 и так далее. И построим меру как? Ну, мера числа 1 равна оси x1, мера числа 2 равна x2 и так далее. Получится сигма-аддитивная мера. Вот. И вот это подпространство сигма-аддитивных мер, оно строго меньше, чем пространство всех комплексных мер на 2 в степени n. Это не то, чтобы совсем очевидно, это, в общем, некое утверждение, но тем не менее оно действительно будет строго меньше. Ну, я даже определение еще не стер. Смотрите, там конечные дизъюнктные объединения, а там счетные. Разница все-таки. Да. И вот в этом разница. На самом деле, конечная аддитивная мера, которая не является сигма-аддитивной, это нечто, чего нельзя потрогать. Они существуют, но потрогать их нельзя руками. Вот их таких конструктивно хороших примеров конечно аддитивных мер, которые не являются сигма-аддитивными, их нет. То есть их можно из некоторых общих соображений вывести, что они на самом деле существуют, и их очень много. Но вот руками прям построить, предъявить явную формулу и сказать, вот вам не сигма-аддитивная мера, так делать не получается. Это так с некоторыми теоретико-множественными тонкостями связано. Но они бывают, такие меры. И вот тут как раз тот самый случай. Мы должны брать все меры здесь, в том числе и не являющиеся сигма-аддитивными, чтобы получить двойственную бесконечность. Okay, so let's continue now our discussion. So from now on, we assume that X is not just a set, but is a compact Hausdorff topological space. And we consider the Borel sigma algebra. So we denote by the following symbol, the Borel sigma algebra. The Borel sigma algebra on X. So formally, this is the smallest sigma algebra containing open sets. A sigma algebra generated by open sets. And we give the following definition by a Borel measure on X. A Borel measure on X. By Borel measure, we mean a sigma additive measure, a sigma additive complex measure on the Borel sigma algebra. Sigma additive complex measure on the Borel sigma algebra. So since X is a topological space, it's reasonable to consider only those measures, only those Borel measures, which are in a sense compatible with the topology. So we say that a Borel measure mu on X is regular, or is a Radon measure, if it satisfies the following condition. For each Borel subset B of X, for each positive epsilon, there exists a compact set K contained in B and an open set U containing B, such that the measure, the variation of mu, of U minus K is less than epsilon. So this condition means that each Borel set can be approximated by a compact set from inside and by an open set from outside. And in fact, it's a simple exercise to show that, in fact, it's enough to require the existence of K only or of U only. But the most convenient way of writing this definition is the following one. So roughly, the meaning of this definition is that mu is regular if it is compatible with the topology in this sense. In fact, this regularity condition is automatic in many concrete cases. So here's a useful exercise. If X is metrizable, then each Borel measure on X is regular. So this regularity property is meaningful only for non-metrizable spaces. Otherwise, it is just automatic. And by the way, the proof of this exercise is almost identical to the well-known fact that the Lebesgue measure on Rn is regular. The proof for an arbitrary metrizable compact space is essentially the same as the proof for Rn. Okay. Let's now consider the space of all Radon measures. We denote by M of X the space of all Radon measures on X. So it's a vector subspace in the space of all Borel measures and the space of all finitely additive measures of bounded variation on the Borel sigma algebra. This is a vector subspace. It's a simple exercise to show that a linear combination of two regular measures is again regular. So it's a vector subspace. And now we can state the following fundamental result. This is the so-called Riesz-Markov-Kakutani theorem. If X is a compact Hausdorff topological space, then the map from M of X to the dual of C of X, which takes each Radon measure mu to the respective integral with respect to mu, is an isometric isomorphism. An isometric isomorphism. The theorem is rather non-trivial, and of course the difficult part is to show that this map is surjective. If we try to use the same naive approach as in the Hildebrand-Kantorowicz theorem, then we fail, because if we define, if we start with a bounded linear function on C of x, and we define a measure in this way, then in general, the resulting measure will not be sigma additive. So this doesn't work, and we have to prove the surjectivity in a slightly different way. There are several proofs for this result. For example, the most, in a sense, elementary proof, which is based only on some basic ideas from measure theory, can be found in the famous book by Danforth and Schwarz, Linear Operators. But the proof is elementary, but it's quite long. There is a much nicer proof, which is based on some ideas from general topology and on some ideas from Banach algebra theory. Maybe if I have time, I'll prove this result in the next course on operator theory next spring. And by the way, this theorem, one final remark about this theorem, it has a rather interesting history. First of all, it was proved by Riess in the special case where x is the closed interval on the real line. This is 1909. Next, it was generalized by Radon to the case where x is a compact subset of Rn. In the 1930s, Banach and Sachs independently proved this result, assuming that x is a metrizable compact topological space. And the general form of this result is due to Markov and Kakutani. They proved it independently in the end of the 1930s. So the full name for this theorem should be the Riess-Radon-Banach-Sachs-Markov-Kakutani theorem. Okay, so that's all I wanted to tell you about the dual of C of x. So let's now come to the general theory of geospaces. And let's try to ask the following stupid question. So suppose we take an arbitrary normed space. So can we construct a non-trivial bounded linear functional on x? Of course, the functional which is identically 0 is bounded, but can we construct some other examples on an arbitrary normed space? Well, if we think a little bit more, then we understand that this question is not stupid at all. It turns out that the answer is yes. The dual space is non-trivial, and in fact, it is big enough in the sense that it separates the points of our space. And this fact follows from the Banach theorem, which is one of the most fundamental principles of functional analysis. So the statement is as follows. Suppose that X is a semi-normed space. As usual, over the field of real or complex numbers. Actually, we will use this theorem only in the case where X is a normed space. But I'll prove it in a slightly more general case. The proof is essentially the same, or exactly the same as in the case of normed spaces. But there are some situations where it is convenient to work with semi-norms. Again, this will be clear after we discuss locally convex topological vector spaces in our next course on operator theory. But in this course, we will use this theorem only in the case of normed spaces. So we suppose that X is a semi-normed space, and suppose that X0 is a vector subspace of X. And suppose that we have a linear functional, f0, defined on x0, satisfying the following condition. So it is dominated by the semi-norm in the following sense. Then there exists a linear functional f defined everywhere on x, which extends f0 such that the restriction of f to x0 is f0, and such that the same estimate holds for f. So briefly, the theorem states that each linear functional defined on a subspace and satisfying this estimate can be extended to x in such a way that the same estimate holds everywhere. I'd like to stress that the most important point in this theorem is this estimate. So if we remove this and if we remove this, then the theorem will be, well, it is true, but it is rather trivial. It is very easy to show that each linear functional defined on a subspace can be extended by linearity to x. We just choose an algebraic basis in x0 and extend it to an algebraic basis in x. And so now it's very easy to construct such an extension. So the point here is this estimate. So if it holds on x0, then we can find an extension which satisfies the same estimate everywhere on x. So our strategy for the proof will be as follows. First of all, it will be convenient to prove this theorem in the case where k is the field of real numbers. And then we will reduce the complex case to the real case. So first of all, we give a proof for the case where k is the field of real numbers. First of all, we consider the following special case. Let's assume that there exists an element y in x such that the following formula holds. So in other words, we assume that x0 is a subspace of codimension 1 in x. Of course, this is a very special case, but we will see shortly that this is the most important case. Well, in this case, it's very easy to construct an extension. Then for each real number c, there is a unique linear functional f on x which extends f0 and which takes this element little y to c. This is more or less obvious. This follows from this direct sum decomposition. So we want to find c in such a way that this estimate holds. Well, first of all, we observe that this estimate holds everywhere, if and only if f of y minus x is less than or equal to the semi-norm of y minus x for each x in x0. So these two statements are equivalent because each element in x, which is not in x0, has this form up to a multiplicative constant. So if we prove this, if we find c in such a way that this inequality holds, then by linearity, this inequality holds as well. Okay, now what is this? F of y minus x is c minus f0 of x. And this should be less than or equal to y minus x. And it will be convenient to write this inequality in a slightly different way. So this inequality means that C is less than or equal to f0 of x plus the norm of y minus x. And is greater than or equal to f0 of x minus the same number. For each x in x0. So all the numbers are real, so we can write this inequality in the following form. Okay, now, so we are interested in the existence of such a constant. When does it exist? Well, clearly such a constant exists if and only if all numbers of this form are less than or equal to all numbers of this form. So such a constant C exists if and only if for each pair of elements x1 and x2 in x0 we have the following inequality. So here's a picture. This is the set consisting of all numbers of this form. And this is the set consisting of all numbers of this form. So if they are in such a position, we can take just any number C in between, and it satisfies this property. Okay. So to show that this is indeed the case, to show that such a constant exists, we write this formula in the following way by using the linearity of f0. So f0 of x1 minus x2 is less than or equal to y minus x1 plus 1 minus x2. But by assumption, f0 satisfies this condition. So f0 satisfies this condition, and so f0 of x1 minus x2 is less than or equal to the norm of x1 minus x2. But by the triangle inequality, this is less than or equal to x1 minus y plus y minus x2. And what we get is precisely this inequality. So as a result, we see that this condition is satisfied. And so there is a constant C satisfying this condition. As noted by star. There exists a real number C satisfying condition star. So we see that we have proved the Hahn-Banach theorem in a very special case where x0 is a codimension 1 subspace. And the general case will be discussed at the beginning of the next lecture. So at the next lecture, we finish the proof of the Hahn-Banach theorem for the real case. Then we reduce the complex case to the real case, and we discuss why this theorem is important. It is important because it has many important corollaries. Okay, that's all for today. Thank you.